right, you're clear to go.
Thank you very much. Once again, thank you, everybody. Good evening, and thank you for having me. My name's Peter, and just as a very short introduction, currently I'm working in Cisco, and I'm the guy responsible for the CCIE Enterprise Infrastructure exam. So if you ever go for it around this time and you don't like it, you know to whom to complain, because that's me. Before I did this, I was 3 years working in the tech team for DC switching. And before that, I had some university career as a university teacher. And EIGRP happened to be my favorite topic. So somehow all the stars aligned that I'm now here today. And today, regarding EIGRP, I would like to talk about the way it computes the best paths and it computes the metrics, because there is a lot of quite arcane vocabulary when we talk about feasible distances and reported distances and successors and feasible successors. And there is something going behind the scenes that no other routing protocol has. And so I'd like to touch those topics. Questions will come. Just please shout and ask anytime you feel you have something to ask. I'd love to have this session to be interactive. So it's probably known that EIGRP comes in with a complicated way of computing metric. Some people call it the composite metric, some call it the multivariate. And this owes to the old IGRP that was designed to try to take something more smart into account rather than just the hop count. And the old IGRP was designed to take into account they wanted to take into account 5 properties of a possible path to a destination. And I'm just going to list them down in some kind of an editor. So let's say for example here, and I'm going to make this again a logic. So one of the parameters is bandwidth, and we take the minimum bandwidth along the possible path to a destination. Now, EIGRP doesn't really know how the whole network looks like, so it doesn't know link by link by link what is their bandwidth when I'm standing somewhere in the network. Rather, it always takes the information about the bandwidth that is received in an update that EIGRP sends from router to router, and it looks whether the incoming interface through which the update came has its own bandwidth smaller than the one that is indicated in the update. And it always takes the smaller one out of these two, the one received in the update that one EIGRP speaker told the other, and from the interface where the update came through. The second parameter is delay. Now, delay, this is a parameter that is configured on the interfaces in Cisco iOS using the delay command. And this delay doesn't affect anything else at all. EIGRP is the only system in iOS and iOS XE that takes this delay value into account. So pretty much it's a synthetic value. It doesn't say anything, but EIGRP takes it and it simply adds it across the whole path and looks at the total sum of the delays. The third parameter it takes into account is called reliability. This is a parameter that is dynamically estimated by Cisco iOS on interfaces. And it looks at the ratio of correctly received packets versus all received packets. That's the reliability. And again, we're looking into the minimum reliability because obviously the path with the minimum reliability is the least preferred one. The fourth parameter is load. Now, we're looking at the maximally loaded path because again, if we're taking into account the load, then we would like to avoid the paths that are too loaded. And finally, there is the MTU. I'm trying to remember if we really take the smallest, or I believe it is the minimum. Now, many books say that the MTU is a part of this computation. Truth is that the MTU is advertised, but EIGRP and the old IGRP, where these 5 metrics have been originally designed to be used, they don't make any path choices based on MTU. It's a parameter that's advertised, but there is no choice done based on this value at all. I've heard once a nice way of remembering these 5 parameters or these 5 metrics, and it's this one: big dogs really like me. Big dogs really like me. So bandwidth, delay, reliability, load, and MTU. And this thing is nice to remember, especially if you configure redistribution from another protocol into EIGRP, because then you're required to specify these 5 metrics, and they come in this order. First comes the bandwidth, then the delay, then the reliability, then the load and the MTU when you do the redistribution. So this is a nice way to remember just what are the 5 parameters and what's the order. Now, each of these 5 parameters, out of which only the first 4 can ever be taken into account, they are combined using a formula into a single resulting number that is called the composite metric. There's a bunch of articles out there on internet. They say how this formula looks like. I'm only going to show it to you. Well, let's say Wikipedia, for example. Here's the formula. Now, there will be certainly no exam out there that should be asking just how this formula looks like, because memorizing this makes no sense. And anybody who needs to tweak it somehow understand it. Anybody can find it somewhere outside. So, but this is how it looks like. And you may notice that the formula refers to the bandwidth, refers to the load, to the delay, and possibly to the reliability, but the formula doesn't cover the MTU at all. What comes into this formula, aside from these truly 4 parameters, bandwidth, load, delay, and reliability, are constants that are called K1 through K5. These are called the K values, and essentially they are weights. And by tweaking them, you can change how strongly each of these parameters influences the overall metric in EIGRP. So K1 influences the importance of bandwidth. The higher the K1 is, the more impactful the bandwidth changes will be to the overall computed metric. K2 refers to a ratio between bandwidth and essentially a remaining capacity of the path. So K2 is something that refers to the remaining utilization of the link, so to say. K3 relates to delay, and both K5 and K4, they refer to the reliability. There is no K here that would refer to MTU. There is no MTU in this formula. Importantly, by default, the K values are set to, well, K1 and K3 are by default set to 1, and all other K values are set to 0. So essentially, the metric computation collapses to the sum of bandwidth and delay. And for certain reasons that are more engineering rather than or technical rather than any other science behind it, the whole formula is multiplied by 256. So this is what happens by default. We take the bandwidth into account and we take the delay into account, multiplied by 256, and this produces a total number that's called the composite metric. Between EIGRP speakers, the K values must match. If two EIGRP neighbors have the K values set differently, they will not come up as neighbors. They will keep complaining in logs that they have their K values mismatched, but they will never establish an adjacency and they will never exchange routes. And this is because in EIGRP, we don't send the resulting metrics between the routers. We always send these 5 individual components, and each router is supposed to combine them together on its own. And can perhaps anybody tell me, why is it necessary that we send those metrics split into the components rather than just sending one simple value from one router to another in EIGRP? Any idea?
Not that I could think of.
Okay, here's what happens. If you want, for example, to take the minimum bandwidth along the path, well, imagine that you just sent the outgoing or the resulting number, let's say 256,000. The number 256,000 somehow combines by default both the bandwidth and the delay. Now, how could you split or extract that bandwidth out of the resulting number? There's no way. In theory, there's infinitely many ways how you can, how the bandwidth can look like. Exactly because you want to do those per component operations that said that for bandwidth, you need to take the minimum from the received one and the one on your interface. That the delay has to be a sum of all the delays from the update and on your interface. Because the reliability has to be minimal, because the load has to be maximal, and the MTU has to be again minimal, you have no other way than to send these 5 parameters one by one in the update and do all these minimums and sums and maximums locally and only locally combine them into the resulting number. And when you then share the route with other routers, with other neighbors, you need to again send them split into components. So what EIGRP advertises from router to router are always these metrics individually, and each router combines them only locally together, but it never shares the combined number. It always shares only the components. This is seen nicely in the topology table. And so that you have an idea what network I'm running here, this is how it looks like. Essentially, I have 5 routers called R1 through R5. I will be standing most of the time on the router R1 on the very left and looking at different paths that have been received across from the neighbors. And just so that you get a little used to my addressing, I like to use addressing that's from the 10/8 private space. Now these 10.255.255 /32, these are my loopbacks. So anytime you see 10.255.255, these are loopbacks. They will have obviously a net mask of 32. And the last byte or the last octet is the number of the router. So each of these loopbacks here belongs to the respective router. This is from R1. That's why, because I'm standing on R1, this is the directly connected. And then I have the loopbacks from the remaining 4 routers that came from the EIGRP. And regarding the networks on the links between the routers, I'm using 10.0. Now the 3rd octet tells me between which 2 routers the network exists. This is a network between router 1 and router 2. This is a network between router 1 and router 3, a network between router 1 and router 4. Coming back to the diagram, these would be these links. This guy here, this is the 10.0.12. This is the 10.0.13. This is the 10.0.14. And you can guess, this guy here would be 10.0.25, 10.0.35, and 10.0.45 here, this guy, this link. All right, but I wanted to come back to those metrics. So if I pull out the EIGRP topology table, this will be the knowledge of EIGRP. Now, the topology table, personally, I like to think of it as a working store of the EIGRP process hidden on the router. It's not just best paths, it's all paths. Everything that EIGRP knows about is stored in the topology table, and all path selections are done based on the data here. So in a way, it's something similar to a link state database in OSPF, although EIGRP doesn't really know how the network looks like, as opposed to OSPF that exactly know how many routers and how many links and between which routers they are there. Now let me pull out a specific record of a network. And I'm standing on the router 5. And for example, let me pull out information about a loopback that's located on router 2. And notice here, I'm going to highlight it for a moment. These are the individual metric components spelled out individually. There is the minimum bandwidth here. There is the total delay, reliability, load, MTU, and guess what? We also have hop count. So even hop count is being accounted for, although it's used only as a fail-safe. And again, just like MTU, EIGRP doesn't change or doesn't really make any path choices based on the hop count. You can just set up the maximum hop count, after which the route will be ignored and advertised as unreachable. By default, it's 100, and you can increase it up to 255, obviously, but by default, it's 100. But again, even though we account for it, and we have it, we do not make any path choices based on the hop count in EIGRP. If I pull a network that's farther from me, so let's pull the loopback network from R5. I should be seeing a hop count of 2. Let's hope I don't get disappointed. Yep, hop count is 2, obviously because I need to go through 2 routers. So once again, we have the bandwidth, delay, reliability, load, and MTU. And just to conclude a thought here, if I pull out an interface data counters show interface, for example, E01, those values are here. This is the MTU, this is the bandwidth, this is the delay, reliability, and load, which iOS really splits into transmit load and receive load. And I believe that we take the receive load into account. It's very rarely done in the field that the K values would be changed to take load and reliability into account. Most of the time, you'll find documents saying don't touch the K values and change them only if Cisco Tech tells you so, or Cisco Professional Services test it for you and tell you so. And it's mostly good because simply the best practices and the real life experience has shown that most of the time doing the choices based simply on bandwidth and delay are okay. And there's even more important thing to say. Even if we configure the EIGRP to take the load and reliability into account, these are not really monitored on the in real time. They are taken into account only when another update is being sent that was triggered by topology change, like a link came up, link came down, neighbor came up, came down. But just because a reliability changes or just because a load changes, EIGRP is not going to send out an update. Because if we did, then imagine with load, it would be pretty dangerous. So you have an unloaded path, which would have a smaller cost. So EIGRP would decide to move the traffic over to the unloaded path. Then another, well, let's say the other path that was used before will become unloaded. So after a time, EIGRP will swing back and move the traffic back because now that path is the cheaper one. And you could end up with EIGRP oscillating between various paths simply because it shifts the traffic away, thereby making the path cheaper and then returning back to it only to make it costly again. So the load and reliability are not really useful that much. And this is simply a legacy of EIGRP trying to be an IGRP drop-in replacement. So IGRP would have its periodic 90-second timer with updates. And EIGRP trying to be compatible, so configuration-wise and metric-wise, it just took over those metrics, but they don't make as much sense in an event-driven protocol such as the EIGRP. Gentlemen, so far so good?
Absolutely.
All good so far.
So when you say event-driven, are you talking about, let's say, loss of prefixes, topology changes, and things like that?
Exactly. When EIGRP doesn't, well, if nothing in the network changes, like no link comes up, no link comes down, no neighbor comes back online, nobody adds a new network, nobody changes addressing. If the topology stays the same, EIGRP has no update to send. In fact, that's one of the reasons why protocols that don't want to be driven just by timers like FRIP or IGRP have to use the hellos, because if you have no update to send because nothing's happening, then you are silent. But from that point of view, if you're silent, I don't know if you're alive and just have no updates or if you have died. So that's why the hellos come in, because you need to send me something to convince me you're still there and you're silent simply because nothing's happening. And that's how EIGRP works and OSPF too, in that if there is no change in the topology, they're silent, they don't send any updates. Now, OSPF has to refresh the LSAs. By default, it's done roughly every half an hour. EIGRP is even more silent if there is no update. It just sits there completely silent, and hellos are the only packets that are ever exchanged between EIGRP speakers. Okay.
Good deal.
Let's come forward. Now, in EIGRP topology table, there's a bunch of information about these networks. And these numbers here, well, they are pretty ghastly to look at. These are the computed distances, well, distances computed by taking those component metrics into account. Now, I've intentionally did one thing in my configuration here, and I'm going to show the config section EIGRP. This is how my EIGRP config looks like. I'm using the named mode for EIGRP configuration. And I have intentionally changed the K values to take only the delay into account here. I've done it for two purposes. First of all, it makes the numbers smaller because I'm not adding the bandwidth component to the overall metric. Second, though, the bandwidth in the EIGRP metric works in a little counterintuitive way. The thing is that because you always take only the minimum bandwidth into account, then if the bottleneck isn't your interface, but somebody else, then changing your interface's bandwidth is not going to have an effect on the path that you're trying to influence. Because once again, we're taking the minimum bandwidth into account. And if the bottleneck, the smallest bandwidth, isn't at your interface, then changing your interface's bandwidth isn't going to influence the metric of the path overall. Now, while it's logical, it's also not intuitive. And especially when looking into basic EIGRP behavior, I like to avoid these things. And that is why I have changed the weights and the K values here so that only the K3 is set to 1. So I'm only taking the delay into account and nothing else. If somebody is counting the zeros here, well, the 0 here, this stands for type of service 0. It's a mandatory parameter that you have to put into this command, metric weights, but it's the only allowed value there. In the times long past, it was thought that for different IP type of service values that could be from 0 to 7, you would have separate routing tables. So every IP type of service traffic would have a separate routing table, possibly with different K values and so on. Well, that was never implemented, and we don't really use the IP type of service anymore. We have differentiated services code points. But the syntax of the command state, so the 0 has to be there. And then come the K values. This is the K1, K2, K3, K4, K5, and well, lately there's also a K6, they call it extended attributes, but it has only been envisioned to be used in what they call the MANET networks, mobile application networks. Otherwise, if you're not in a MANET network, the K6 isn't used anyway. Coming back to the topology here. So these are the computed numbers. And I'd like to somehow explain all the numbers that we see here. And let me take this output here, copy it, and maybe put it into an editor and play with it a little so that I can explain what are those numbers that we're looking at here. So first of all, let me look here into these brackets. The first value that's shown here is called the computed distance. Then is reported distance. And the computed distance, the first one, the number before the slash, this is the total distance from the network that I'm looking at, in this case 10.255.255.5/32. This is the total distance through a specific neighbor. Now I'm showing two neighbors here. This is neighbor 2, this is neighbor 3. So the total distance or the total cost or total metric, they all mean the same thing. The total distance through these neighbors to reach that network is the number before the slash sign. So it would be the 7 something through neighbor 2 and this 111 something through neighbor 3. That's the computed distance, and once again, that's the total one from me through my link to that neighbor, and then through whatever path that neighbor needs to take. Since I'm distance vector, I don't know how that path looks like. I know only the distance of my neighbor. The second number after the slash sign here, we call this the reported distance. Some older textbooks, some older courses and trainings may also call this the advertised distance. Advertised distance and reported distance are the same thing anytime you see the advertised distance, but since it gets confused easily with administrative distance, the name advertised has been abandoned. So we call it reported distance nowadays. And this is the distance of the neighbor. So that is how far that neighbor is from the destination. And this is how far I am from the destination through that neighbor. Essentially, the difference between these two is simply the cost of the link between me and that neighbor in EIGRP terms. The computed distance and reported distance will be there for a destination network and every single next hop that advertises it to me. So that's why through all these via lines, I have a separate pair of computed distance and reported distance. And there is one more. It's called feasible distance, FD. Does anybody know what a feasible distance is? Any idea?
Is that like the best route? Like that's something like that, the best, the shortest distance?
Yep, it definitely looks like it because this number is really this one here. Well, in this line here, these two numbers seem to match.
That's right. Yep.
But let me do something here. I'm going to go to, and I know I'm a little stretching the time here, but if you don't mind, I certainly don't. Once again, I'm standing on router R1. That's where I'm looking at the network. And in fact, I have intentionally also engineered the delays on these links. And just to explain what I did there, I'm just going to take this text and edit it. So, and I'm going to even make this text a little larger so that we can see it even easier. Just this graphical editor is a little simplistic, so sometimes it plays tricks on me. Okay, so the numbers I'm going to simply show by these links are the setup delays, which makes it also simple to look at the topology. So I've set these delays to 5. The delay between 1 and 3 I've set to 8. And so also I did 8 here. And here, let me see what I did there. Here's the delay 2. And this delay here is 11. And finally, the delay here, this is essentially just a loopback, is 1. So by the way, that's also the reason why the path through 2 and path through R3 did not have the same metric or did not have the same cost in the output we have been looking in here. Notice that this is through 2, this is cheaper. Through 3, this is more costly because, coming back to the diagram, if I just looked at the sum of delays and didn't do the multiplication there, the total delay from R1 through R2 to R5 would be 11, 5 plus 5 plus 1, while through R3 would be 16 plus 1, which is 17. Alrighty. I wanted to show something about the feasible distance. So now it's this value. Let me come back to router 1 So here we are. This is the interface 0, 1 that goes to router 2, and you see the delay 5 here. Let me do something. I'll go to this interface and I'll change delay from 5 to 7 carefully. I give iOS, it's not the EIGRP that would be slow, more the iOS. It may take a little time to recalculate or notify EIGRP so that it can recalculate. And now I'm going to pull out the topology output again. And just so that we can compare, I'm going to take this output again, just the way I copied it before, come here and paste it again. Okay, now what happened? Notice the real distance through 2 has changed. Now it's, well, it's this 8.5 something. Of course, the reported distance from R2 hasn't changed. I didn't touch that guy. So it didn't update me. Why should it? Just the cost of the link between myself and R2 has changed. R3 obviously wasn't impacted at all because I wasn't touching anything that was related to the path through R3. So this path became a little more costly in total terms, but the feasible distance stayed at the last value. It didn't get updated. In reality, feasible distance is not necessarily my momentary best distance. In reality, feasible distance is a historical minimum of my distance to the destination. In other words, it's a record of how close I used to be to this destination at some point in the past, or maybe better said, how closest I was to the destination. And I said, it's a historical minimum. Obviously, there has to be a way to reset this value and set it again. That event, when I can reset the history and just erase it and start from scratch, is when EIGRP goes into the active state for the route and performs what we call a diffusing computation. That's the only moment when we can reset the feasible distance to a positive infinity and then set it to the new minimum that we have. Otherwise, the feasible distance can either stay at its current value or go lower. But if we ever need to increase it, we need to go active. So just once again, the feasible distance is a record that tells me how closest I used to be to the destination in the past. There is no feasible distance that would be computed for a destination and a neighbor, as opposed to the computed distances and reported distances that are always for destination and a neighbor. Feasible distance is there only for the destination itself and is just a record of how close I used to be to the destination in the past. And why is it done in this kind of weird way, you may ask? I guess this would be for another session now. EIGRP has one overarching goal. Never, ever create a routing loop. Never, ever use a neighbor that could, even for a short period of time, return packets back to me, either directly or through a detour. But since EIGRP does not know how the network looks like, it needs to use some, well, let's say, help rule or helping rule that can guarantee that if I choose a neighbor, I can be 100% certain that the neighbor is not going to return packets back to me through a routing loop. And this rule is called the feasibility condition. And the feasibility condition takes into account the neighbor's reported distance and my own feasible distance. And you probably heard the rule before. The rule says that if the reported distance is smaller than my feasible distance, then the neighbor is loop free. And we call it the feasibility condition. Yeah, well, written like this, it looks horrible. Myself, I have trouble remembering this. Well, just what way does the inequality go? But let's say it in a more human way. The feasibility condition really says, if you are closer than I have ever been, then you aren't going through me now, and you couldn't have gone through me in the past. So you have to be loop free. Once again, if you are closer than I have ever been to the destination, you're not going through me, not now and not in the past. So it's safe to use you. This is how the feasibility condition works. And every single path choice in EIGRP is subject to this feasibility condition because we want to be loop free. And that is exactly why we need the feasible distance to be a historical record rather than the momentary distance. Because if it was momentary distance, we will be doing exactly the same choices as RIP. RIP always compares my distance versus your distance. There is no historical record. Well, and we know very well that RIP is prone to routing loops. If EIGRP did the same thing, it would be no better. Okay, since we are already up to the allocated time, I don't want to stretch it more. I could talk, but that's up to you, gentlemen. But I would personally stop it here, but I'm happy to take any questions.
Yeah, I got it.
Go ahead.
Yeah, Peter, when you were changing, you were on router number 2, and you changed the delay from.
Pardon me, I was on router number 1.
Okay, you changed the delay. Yeah, you changed the delay from 5 to 7.
Yeah.
Is it understood that the unit of measurement when it comes to that delay's time is that in microseconds?
So, okay. Now, this value here is a unit that contains, well, delay 1 means 10 microseconds. It's ridiculous. It's tens of microseconds. If I show you the delay of the interface E10 now, show interface E10, it says 70 microseconds. So a unit inside the delay command is really a unit of 10 microseconds. Nobody cares because in reality, this number is not used by anybody else rather than EIGRP. And for EIGRP, again, it's just a number that it adds together. So we can talk about microseconds, and the wide metrics, in fact, are counting the delay in picoseconds. But it's almost just an academical exercise to talk about what units is it. It's a virtual time scale, really, and that's the best way of looking at it.
Okay, appreciate that.
I got a question, Peter, if you don't mind.
Absolutely, go ahead.
Great. And when you were referring to the active state, when we had to change, you said something to active in order to update. I guess it was the feasible distance.
Mm-hmm.
What does that mean? And I guess how will we change it or set it up into an active state?
This is in EIGRP's full control. It's not something I can trigger just by a command. So here's the thing. We say that, well, it's the terms passive and active go to EIGRP's activity whether it needs to do something to find a new route. If a route is passive, EIGRP is happy with it because it doesn't need to search for a new path. A path is active if EIGRP is currently in the process of searching a replacement route for the destination. A route in the passive state is a good one because EIGRP is happy with it and doesn't need to fix it. A route is an active state if EIGRP needs to fix it by searching for something, for replacement route. And although, unfortunately, we probably don't have time right now, EIGRP does two types of computations, really. If EIGRP can simply flip from one next hop to another based on the data that is here in the topology table, this is not called an active state because the change that you do is only local. You don't need to synchronize and coordinate with your neighbors. You just replace the neighbor, and if your own distance changed as a result, you send an update to your neighbor so that they know. By the way, the update only contains your change distance, nothing else. But it may be that because we have a feasible distance that is too small to pick another neighbor because of that feasibility condition. So what I'm saying here is you have a neighbor, or maybe let me do it like this. Topology. Do you know the all links parameter here? It's going to be a little different now.
Okay.
Now you see all the neighbors here for the network. We haven't seen, pardon me, the four before. Well, the guy here, the four, for example, this guy here, the way they are sorted here, the router 2 provides the shortest path. The router 4 provides the second shortest path. The router 3 provides the third shortest path. But if we were talking about the feasibility condition, then the reported distance of router 4 is not smaller than my own feasible distance. That's why I didn't share in the output without the all links parameter. And this means that the router 4 is not really trustworthy. I don't know what this number means here.
Okay.
I cannot be certain that the guy doesn't return to me because let's make those numbers simpler. If my feasible distance is 10, and your feasible number and your reported distance is 15, so I am 10, you're 15. What does your 15 mean? Are you going through me, and is the cost of the link between you and me 5? Because that would add up to 15. Or are you bypassing me, and just that bypass is 15 units of the cost?
So you just bypass it.
I see, but see, just from the number, I cannot tell because both options are possible. And I'm not taking chances. EIGRP doesn't take chances. EIGRP is either 100% certain or it needs to ask. And that's what would happen here.
Okay.
If 2 failed, if number 2 failed, we wouldn't go to 3 just because it meets the feasibility condition, because we have somebody here who can provide a shorter path, but about which we aren't certain. This is when we would go active, send those queries, and ask, hey people, my current distance is this one. Does it influence you? Take this into account and confirm. That's really the query. And we would wait till all the queries come back. The replies to all queries come back. And then it would take a choice. And that's when, for me, the active state and this what we call the diffusing computation will be concluded. Then and only then, I can reset the feasibility distance and start from scratch. Like showing you the diffusing computation, the query process would be a wonderful thing for the next session, I would say, because there is something to show for the next 30 minutes.
Cool. Well, thank you for that explanation. That was really detailed. So that's great, Peter.
Very much welcome. Very much welcome. Any other questions?
I have one. How does EIGRP behave with IP version 6?
Exactly the same way, because the only thing that has changed is the transport. We use IPv6 instead of IPv4. But since, pardon me, since EIGRP has its own transport protocol, Claude spoke about it in the last session, what we call the reliable transport protocol, RTP, that one stays the same. So obviously the neighbors are shown as IPv6 neighbors, but all the remaining logic, the whole engine stays the same. It's just like changing winter tires to summer tires. The car is still the same, and all the rules are exactly the same.
Okay.
Any other question?
If you got the time,
Yeah,
can you tell us what type of battle station you have and what type of lab do you have?
Type of, pardon me, type of what?
Battle station, your workstation, computer, laptop.
Battle station. Well, I'm definitely a PC guy, and this is a Lenovo P15 that I'm working off of. But what you see here is a Debian Linux running in VirtualBox, because I'm really a Linux person, so I love to have a Linux somewhere. Now, if it was easier, I would have been running Linux barebone on my laptop, but the way, because of the drivers and everything, it's easier to keep Windows on the laptop and run the Linux in a virtual machine, just like this one. And what I'm using here, this topology here, since I'm a Cisco guy, I can use the IOL. So these are really IOL processes. But if I didn't have access to those, then I would be probably most likely using the Viral or CML2 Personal Edition, because the images there are essentially almost the same as these ones. So up-to-date versions. And definitely easy to create topologies around them.
Okay, thank you. Thank you.
Very much welcome.
And Peter, I just wanted to say again, thank you so much for taking the time. I know it's roughly 1, 2 a.m. where you're at. And again, thank you so much. And with that being said, I'll go ahead and close the meeting. And guys, again, this is recorded. This will be uploaded to YouTube and LinkedIn. So again, thank you so much. And Peter, last question: Can the guys on this channel connect with you via LinkedIn?
Anytime. I'll only be happy to.
Yeah. Awesome. Well, guys, this was great. I'm going to let everybody go, of course, and let Peter get some sleep. I'll go ahead and close the meeting for now. You guys
Definitely
have a great night,
appreciate it.
okay?
Definitely.
All right, thank you so much, Peter.
All right, many thanks.
It's been a huge pleasure. Thank you for having me. Thank you.